Good morning, everybody. So I'm Nikolai Matni. I'm a postdoc at Caltech. And so before diving into this, actually, I think it's worth maybe giving a little bit of background about myself because I'm a bit of an outlier at this workshop. And the talk is going to be very different from all the other talks we've seen. So my background is in control theory. And I've only really recently started working on networking in SDN probably the last 6 months. So it was a real pleasure to be invited here I've really been enjoying the talks and learning a lot. And what I want to share with you today is some new theory that we've been developing in the control theory community that I think will be of interest in the sense that now with SDN, we can actually start thinking about applying these ideas in the context of networking, whereas prior to that, I don't think we could do that. So my title has a whole bunch of different words and concepts in it. I think I was a little bit overly ambitious when I submitted my title and my abstract in the sense that when I put together my initial slides, my introduction took about 20 minutes. So I have 15, so I'm going to make a title change on the fly here. And I'm really going to focus on ideas from distributed optimal control theory and how maybe those can become relevant in the context of SDN. So I don't want to assume any background of anybody here. So I'm going to start with probably about a 5 to 10 minute tutorial on what control theory is and why that would be relevant in this context maybe. And then with whatever time I have left, I'll talk about a use case that we actually we actually implemented. And so this is joint work with my advisor and John Doyle at Caltech and some folks at Cornell, Kevin Tang's group there. So control theory. If I had to describe that in one sentence, it would be the use of feedback to mitigate the effects of dynamic uncertainty on a system. So undesirable effects due to things that we can't predict. So I'm going to use a really simple toy example here to introduce some of the basic concepts. And one of the things that I want to contrast is the idea between a stabilizing controller and an optimal controller. And what I mean by that, I'll make clear in a few slides. So the kind of object of central importance in control theory is what we call the plant. And this is just the system that we want to make behave well. So I'm given a plant. For this example, we're going to use an airplane. So given this plant, I'm going to specify a set point. So this is a desirable state that I want to keep my system at. So for an airplane, this would just be keeping, say, a constant pitch in spite of, say, wind gusts, right? So I can't predict these wind gusts ahead of time. And so if I don't do anything clever, then I'll get what's called an open loop response. And this could lead to a pretty unpleasant experience. So in control theory, what we do is we close the loop around the system. So we do this by attaching some sensors. So in this case, it would be, say, an accelerometer or a gyroscope. These sensors provide a controller with measurements. And this is a controller that's not an SDN controller. So kind of we're going to have to be careful here. And I'll be really clear to make sure that to contrast when I'm talking about a control theoretic controller as opposed to an SDN controller. So this controller gets access to these measurements. It knows the set point that we want to keep the system at. And it also has some dynamics. So in this case, it would be, say, the equations of motion of an airplane. And it uses all this information to compute a control action, which is then applied to my system via what we call actuators. This is just something that lets me actually change the state of my system. So think of wing flaps moving around or engine thrust. And the goal here is to compute a good control policy so that we use this feedback of measurements to close this loop and limit the effects of disturbances. So one thing that I want to emphasize here is that the heavy-duty computation is an offline one, is in determining the actual control policy of the controller. Online, all we're doing is basically matrix multiplications of measurements that we're getting to compute this control action. And maybe we have to maintain maybe a little bit of state and memory to estimate what's going on in the system. That's about it. So this has nothing to do with networking. Maybe a little familiar, something of a familiar example that can be interpreted, at least from a control theoretic perspective, is TCP. So here the feedback is, I'm seeing either round trip times or drops or queue length, depending on the variant. And the control action is affected by modifying the window length with this AIMD approach. And so about a decade ago, there was a really nice observation that you can actually interpret TCP as a stabilizing controller around the optimal solution to this network maximization problem. But what I want to emphasize here is that it's a stabilizing controller in the sense that we only get steady state guarantees. I can guarantee that I'm going to converge to some optimal value, but I can't tell you how I'm going to get there. So I want to just contrast, emphasize this point of stabilizing controllers only giving asymptotic guarantees. And I'm going to go back to my toy airplane example. So I'm going to show you two examples of a stabilizing controller. The first I'm going to call my first class controller. So I get a little gust of wind, I move a little bit, but I get back to where I started. Now I'm going to show you another stabilizing controller, which I'm going to call the lose your lunch controller. Again, this is a stabilizing controller. I give my system a kick, I wiggle all over the place, and then I get back to where I started. Now, clearly, we really want to be able to pick out controller number 1 against controller number 2. This could be the difference between, say, a fault in your system leading to wild oscillations in traffic pattern, and you needing to over-provision a lot, for instance, or not, right? So you want to be able to not just determine where I'm going to go, but also how I get there. And so the way we measure the goodness of a controller is by quantifying how much it's able to minimize the amplification of a disturbance, right? The first one, I give it a little kick, it barely moves. And then the lose your lunch controller, I give it a little kick and it goes all over the place, right? So we formalize this by capturing the amplification of a system in terms of some cost function that's going to be a function of my error, so how much my system deviates from this nominal set point, the amount of control effort that I actually have to apply to the system to make sure that my system doesn't deviate, and it's going to be a function of my disturbance. And then I'm going to try to minimize overall possible control actions to minimize this amplification. Now, my cost function here it depends on my disturbance, and I mentioned earlier that the reason we want to use feedback control in general is that we don't know disturbances ahead of time. So we have to embed our disturbance in some kind of model class. So you could imagine that I would think of a disturbance having bounded energy, so a wind gust, for instance, would have a bounded energy, or have bounded magnitude. And then we can talk about minimizing the worst case amplification, for instance. If you don't like this kind of deterministic worst case approach, you could also consider a stochastic approach. So you can model your disturbance as, say, white noise, and talk about minimizing, say, the expected value, the average amplification. Right? So you would pick a typical choice of this cost function, then would be a quadratic one, so you're minimizing the variance of your system around where you want to stay. Okay. So any questions on that before I keep going? Cool. And so what I've been talking about, this single airplane example, is an example of what's called centralized control. So in centralized control, there's one system, there's one logically centralized controller that has global access to all the measurements and global control of all the inputs. So this maybe starts to look a little bit more like an SDN problem. You can think of the plant as the network that you're trying to control. And now your SDN controller this controller sits inside of your SDN controller. But one thing that makes control challenging in reacting to these systems is that oftentimes, if there's a lot of latency in this loop, you have poor performance. You can imagine that if something bad is happening in your system, and there's latency in how quickly you can react to it, the longer you have to wait before you can change anything, the worse it'll get. So that's the observation that I have there. And so this has motivated people in the control theory community to consider the case of when I have a large-scale system and there's potentially a lot of latency involved in in acquiring global measurements, computing a global control policy, to look at a distributed setting. So I'm going to relabel things with just their initials and shrink it down. And so the picture in the distributed setting is really that I have a whole bunch of these. And they're interconnected both in terms of their dynamics. So you can think of the plant here as different, say, switches or routers in a network, and these black cables as cables between them. And then I'm also going to let my individual subcontrollers talk to each other. And so the challenge here, from a technical standpoint, is that my controllers now each individual subcontroller doesn't have global access to system information. They each have access to their own subset of system information. And it turns out that this actually ends up being an intractable optimization problem. If I want to solve for the optimal controller in general, something really simple, something seemingly simple, ends up being intractable. One of the big breakthroughs from the optimal control theory community in the last, say, 10 years is understanding what settings we can actually solve this problem exactly. And it turns out that if my different subcontrollers can talk to each other fast enough, then this ends up being a convex problem. So from a networking perspective, I get a convex problem if I give control packets priority through the network. So if my control packets get kind of sent through the network ahead of regular traffic, then these communication constraints are satisfied, and then this again becomes a tractable problem. So in that setting, and so what I want to do now is show an implementation of using these ideas from distributed optimal control theory to traffic control in a wide area network. So I'm talking about distributed optimal control in a wide area network. So the first caveat here is that the problem that I'm going to be posing here is not a standard one. It's not one that you've probably seen in any networking problems so far. I'm also not claiming that this is necessarily the killer application of these ideas, but I think it's an important proof of concept in the sense that we can actually use SDN now to implement these types of controllers that allow for the control of traffic on the scale of round-trip time scales. So the setup is we're going to think about a wide area network, and our traffic engineering problem is going to solve some multi-commodity flow problem using nominal demands between source-destination pairs. And then this will overlay some nominal routing topology onto our physical topology, specified in terms of nominal flow rates on each link between each source-destination pair. Now, of course, even though this traffic engineering problem is solved using these nominal demands, in reality, real traffic fluctuates around these nominal rates. And so, for the purposes of this example, we're going to model these fluctuations as just Gaussians at each time step. There's some work in the literature that suggests that this is reasonable on the order of minutes. We're looking at this on the order of round-trip timescales. There is no data available, so for the purposes of this, I'm just going to ask you to kind of roll with it and just, again, this is a proof of concept in the sense that we can actually build these things. And so the problem that we're going to pose, the optimal control problem that we're going to pose, is what we're going to call the high-frequency traffic control problem. So our controller, our actuators in the system here, are open flow enabled egress buffers. And each of these switches are going to measure local buffer state and flow rate and communicate this with either other buffers or other controllers within the network. And the goal here is going to be to compute a policy in terms of traffic shapers that minimizes a weighted sum between deviations on links of flow rate from these nominally specified flow rates coming from our traffic engineering problem and buffer size. So again, I realize that this maybe looks a little foreign and doesn't really map to perhaps standard networking metrics that folks care about. But I want to maybe show you one slide here that suggests that this isn't a crazy thing to do, in the sense that if I take this weighting parameter lambda here, and I either take it to 0 or to infinity, I recover standard approaches that are used right now. So if I take lambda to infinity, for instance, if I put all of my weight on buffer size, then I recover what I'm going to call the first in, first out approach, which is I'm just pumping out what's in my buffer at line rate as fast as I can. If I take lambda to 0, then I'm only minimizing this rate deviation, and then I recover a policy which I'm going to call a smoothing policy, which is I'm just limiting my traffic rate to that specified by my traffic engineering problem. And so as I vary lambda from 0 to infinity, I get this trade-off curve between packet loss percentage and average queue length. And so you can think of the resulting policy here as a dynamic generalization of these two standard policies. And so this trade-off curve here we generated with just a simple 3-machine test bed at Cornell. So here's the routing topology, one source, two sources, the destination is there. And I have 4 different curves here, and this correspond to 4 different controller architectures. So I want to explain what I mean by a controller architecture, and then show you a final result where we actually implement this in a real wide area network, not just some toy test bed. And so I think one of the questions that SDN brought to the forefront is this question of, should I implement things in a centralized way? Should I keep it in a distributed way? So in the context of this problem, we can actually give a pretty definitive answer. And so I'll show you how we can do that in that context. So I'm going to introduce 4 different controller architectures. The first one I'm going to call the globally optimal delay-free architecture, or the God one. And this is kind of a theoretical construct in the sense that I'm assuming that I have some centralized controller that has 0 communication delay. And this corresponds to really some fundamental limit as to how well I can do. And I can also think about a centralized controller where I have a SDN controller sitting on top of one of these nodes. And all of these switches are just communicating their information to that centralized controller. It's computing this control action and then redistributing it. And so there's latency involved in this collection and distribution of control actions. We can also think about a distributed architecture where each of these nodes has its own little local controller and is taking control actions based on fresh local information as well as delayed shared information. And then finally, we can talk about, and this new theory is really what allows us to compute the optimal controller in this case. And then finally, we can talk about a decentralized or completely myopic approach where I'm only taking actions based on local information. And so this is a non-convex problem, so we just use our best guess in terms of comparing these different architectures to each other. So what I'm showing here now is some results that we have in terms of the max link utilization that we can achieve using these different controllers on a wide area network. So by max link utilization, what I mean is the highest ratio of the nominally specified demand rate divided by the link capacity. And then the traffic fluctuations are given by Gaussians with a standard deviation of 5 or 10 around these nominal flow rates. And we just empirically determined what these ratios were. And so we're exploring the performance of these 4 different architectures. You can think of them as going from most centralized to least centralized, or having the least delay to the most delay. And we see that, for instance, this distributed optimal controller, the one that we can compute using this new theory, allows for the best performance. And the standard kind of first in, first out approach of just pumping things out at line rate actually leads to the worst performance. And the intuition here is that in this distributed setting, we're exchanging information, allowing these different buffers to coordinate with each other, to shape traffic in the right way, to exploit the randomness in these fluctuations. The main takeaway here that I really want you to take away with is that there were no surprises when we went to implement this. It was actually relatively easy to implement. So I think the models that we're using are at the right level. And the ordering of the performance was also what we expected to see. So theory and experiments were consistent, and the implementation was rather painless. So what I want to end with is kind of the high-level goal of what this whole line of research is about, and this is just one small piece of it, is what we're really working on at Caltech is a theory of network architecture that builds on, those of you who are familiar with the network utility maximization framework, it's building on that to introduce these dynamics explicitly into the loop. And so we're trying to understand, can we understand and automate things like deciding where do we need to put functionality in the network? How many layers should we have? How should they interact with each other? What goes in each layer? And should we choose a centralized, distributed, or decentralized implementations? And the takeaway of today's talk was really that we really want to model dynamics and delay more explicitly. And now with SDN, we have the flexibility to actually react to dynamics in a more low latency way. So with that, I'll end, and thank you all for your attention. Please.
So, so the thing is, so you're thinking about centralized controller. This is about where you're gonna get the controller. Is it going to be centralized or distributed or things like that? And based on that, the properties. And the thing about if you want to distribute the controller, there's also the concept of okay, you're gonna distribute the controller to manage a distributed system. And the distributed controller becomes a distributed system itself.
Right.
There's going to be problems if you just control now you have a question of what if there's a fault in the control.
No, absolutely. So especially the example that I gave here, right, which involves really kind of fast timescale updates. The idea of a stateful data plane that Jennifer was talking about yesterday. I think the computation, the online computation is very simple. So it seems like this might be something that is maybe best implemented in a stateful data plane. And then you could still have a centralized controller with a global view of the system that's doing more slower timescale updates. And then in that case, when you have these fast timescale updates happening in the data plane, you have to be careful in terms of how you coordinate these updates in the centralized controller with these fast timescales. But the point that you're making in terms of, yes, there are other trade-offs that need to be considered is absolutely true. And this is, that was one of the reasons why my introduction was about 20 minutes originally. It was talking about all these different trade-off spaces, and this is exploring one slice of that bigger trade-off space, but absolutely. Please.
So sometimes, a lot of sort of network systems applications, there's some inherent resiliency in the application. For example, I think Matt had talked about video streaming and so on.
Right.
There's often buffers and caches and all sorts of things that you can potentially exploit.
Yes.
Have you looked at those kinds of things? How does it fit in?
Right. So one way to interpret the controller that I presented today is explicitly using your buffers as a resource, right? As opposed to just trying to empty them out as quickly as possible, for instance, which I think is oftentimes a common practice. We're sometimes going to hold flow upstream if we know that there's congestion downstream, for instance, right? That's what allowing this communication actually lets you do. So that's one way in which these buffers are being used as an explicit resource. But again, that talk yesterday on again, this hybrid approach of centralized and decentralized, I think is absolutely the right way to do it. And kind of one of the points that I was trying to make here is that if you're you can introduce a different type of local robustness that I think folks haven't been necessarily thinking about because it's from a foreign community. And then you also are going to have to be careful in terms of tuning the interaction between the slower timescale centralized updates and these faster timescale local updates. Please.
So have you tried different types of policies and how it behaves on different settings? For example, if it's, I don't know if you were here in the first talk yesterday.
Yeah.
There are several different policies where you want two different networks to be isolated, or one node cannot be talking to another node.
Right. Yeah. No. I mean, so that would not be something that would fit in this feedback control setting, in the sense that in feedback control, it's one of these ideas where you tell me what the state of the system I want it to be at, and I'll do everything I can to keep myself there. This idea of logically separating things from each other, having different types of policies, is something that would have to be managed, kind of one layer up. Feedback control is really this low-level thing. Could it play nice with these kinds of things? Absolutely, I think so. But that would take some care.
I was thinking in the sense that you could, for example, somehow express a policy and try to keep it that way in some lower level, but...
Maybe we can talk about it offline. Yeah. I think I need to give up my time here. Yeah. Thank you.